Assalamu alaikum. This is your Thermodynamics 2 class, and today is lecture number 25. So, can anyone confirm what's appearing on my screen right now?
Lecture 25
Walaikum
compressible.
salam.
Right.
Chapter number 7, your flow.
Okay, thank you so much. Okay, so as it is mentioned, again it is from chapter number 17, which is compressible flow. And last time we already discussed something related to the flow properties with the change in area. Okay, and we developed two equation in the last lecture, if you remember. Okay, so we will try to continue, and that is for converging diverging nozzle. Okay, so we will try to just move forward on the same topic. Okay, so which is the converging diverging nozzle, and I hope you already know why we are going to study, because this is the main important part of all of your steam turbines, or also or your gas turbines especially. Okay, because there is exhaust section in your gas turbines, and where there is exhaust gases at high temperature released from the combustion chamber, and due to this this part become the most important uh, domain in order to do the thermodynamic analysis. So that's why we are trying to do that, how your flow properties vary with the change in area. Okay, so coming towards the equations, so these two equations we already discussed, and we already derived these two equations. So this equation dA by A is equal to dP divided by rho v square 1 minus Mach square, and dA by A is equal to minus dV by V 1 minus Mach square. So this equation in the last lecture we already derived. Okay, so now we will try to apply these equation for different situations. Okay, and the situation is related to your nozzle and diffuser. I hope you already know what is the difference between nozzle and diffuser. So in the nozzle, our final area is small as comparison to the inlet area, or you can say outlet area is small as comparison to inlet area in the nozzle, and in the diffuser our inlet area is small as comparison to final. So final area is or your outlet is bigger as comparison to the inlet in the diffuser section, because these two geometries, that is nozzle and diffuser, are most commonly used in the exhaust section of your gas turbine as well, and specifically when we are trying to build the exhaust section, we combine these two, nozzles and diffuser. Okay, so the reason you will get to know later on that why we are going to join these two, nozzles and diffuser. Okay, because in order to achieve some specific property, so if you want that your exhaust gas is released at some specific speed at the exhaust area, so that's why you will try to modify it. You cannot just apply the nozzle or diffuser in order to achieve this. So for that you have to combine these two, nozzle and diffuser. Okay, so now we will try to discuss some cases. First is for subsonic flow and supersonic flow. So there's two regimes, that is subsonic and supersonic, and then the cases for nozzle and diffuser. So totally we are going to analyze four cases. Okay, so in this if you can just notice that there are some arrows that is mentioned over there. So if the arrow is upward, so it's mean something is increasing. If arrow is downwards, it means something is decreased. Okay, so in the case of nozzle and subsonic flow, so I am talking about this case. This is for the nozzle and subsonic flow. So as you already know, for subsonic flow, our Mach number is less than 1, and supersonic flow Mach number greater than 1. Okay, so subsonic flow, our velocity increases at the outlet. Okay, so this is basically V. So sometimes we just take it as U, but you can just remember that it is V. So V increases at the outlet. So if V increases, Mach number also increases at the outlet. But pressure decreases, temperature also decreases, and density also decreases at the outlet. Okay, so how these parameters are affected due to change in area, so we will discuss in detail in the coming slide. Right now you just have to know that these parameters are decreasing or increasing. Then if we can just take the supersonic flow, that is Mach number greater than 1, so our velocity at the outlet decreases, Mach number also decreases. That is for the subsonic flow when Mach number greater than 1, and nozzle pressure also increases, temperature also increases, and density also increases. Then if we just change the geometry to diffuser, okay, and if there's a diffuser and there is a subsonic flow, so then your velocity decreases, Mach number also decreases, pressure increases, temperature increases, density also increases. And if we change the flow to supersonic flow, and the case is for diffuser, at the outlet our velocity increases, Mach number also increases, pressure also increases, temperature also increases, and density also increases. Okay, so now the question is how we get to know that these parameters are increasing or decreasing, as there is no hard and fast rule over there that we can say that for this geometry it is increasing or decreasing. So you have to just correlate with these two equations, because these two equations will tell you everything. Okay, so we will try to apply these two equations on all the cases so that you will get some understanding, how these parameters are affected with the change in Mach number or with the change in geometry, that is nozzle or diffuser. Okay, so first thing is that you already know this relation which we developed in the last lecture, I think 1 over rho dp is equal to minus v dp. From this relation we get some understanding that if your velocity increases, and velocity increases, it means dv is greater than 0, okay, and it is positive. So if this term is positive, your dp become negative, okay, because it will be negative term and less than 0. So it means your pressure decreases if your velocity increases. And if your velocity decreases, that for dv is less than 0, if this term become negative, so negative negative positive, so your pressure also decreases, increases, sorry, so dp become greater than 0. Okay, so these two information we get from this equation. Okay, so this is the important thing over there. And now we will try to discuss the cases. So our first case is subsonic nozzle, where the Mach number is less than 1, and nozzle, I already told you that your final area is less as comparison to initial area. So if your final area is less as comparison to initial area, so it means your dA is less than 0, or you can say dA is negative. Okay, so it is mentioned over there that dA is negative for the nozzle. Then it is subsonic flow, so Mach number is less than 1. Okay, so if you can just correlate with this equation, that is dA by A is equal to minus dV by V, 1 minus Mach square, and we put these value into this equation. So from this we can easily say that, okay, so if dA is less than 0, so it means this term is negative, 1 minus Mach square, so Mach number is less than 1, so it means this term is positive. Okay, and then if we can just see from this relation that negative negative cancel and dv become positive, so it means dv is greater than 0 for the case of subsonic nozzle. Okay, so from this equation we can easily find out that your velocity increases. Okay, so here it is mentioned that velocity increases, area decreases because the final area is less as comparison to initial area, pressure decreases. Okay, so how we get to know pressure decreases? From the previous slide, I already told you if your velocity increases, your pressure also decreases, or either you can find out from the another equation which we already developed. So dA by A is equal to dp rho v square 1 minus Mach square. So this equation we already developed. So from there you can also easily judge that your with the change in area and with the Mach number less than 1, your dp become less than 0. Okay, so your pressure decreases. So for example, this term become positive and dA is negative. So if this is negative and rest of this positive, so dp decreases, dp less than 0. Okay, so this is your case for the subsonic nozzle. So similarly, we will try to develop and look for the other cases, that is for the your. Okay, another important point over there is that when there is a isentropic flow with the change in pressure, for example, your pressure decreases, so your temperature also decreases and density also decreases. How this you can figure it out? So as you can already know, your isentropic relation that if there is an isentropic relation, so you can say T2 by T1 is equal to P2 by P1, K minus 1 over K is equal to rho 2 by rho 1, K minus 1. So from this relation, you can easily say that if your pressure is decreases, so density is also affected in the same way, and temperature is also affected in the same way. And if your velocity increases, your Mach number also increases at the outlet. Okay, so now coming towards the second case, and this case is for the supersonic flow, and the geometry is now diffuser. Okay, so same procedure. Uh, So for this case, when there is a diffuser, your dA become greater than 0. So how your dA become greater than 0? Because your area final is bigger as comparison to area initial. So your dA term is greater than 0 in this case. And when your supersonic flow, the Mach number is greater than 0. And if you put all these variables in this equation, so for example, if Mach number is greater than 1, so this term become negative, and if your dA is greater than 0, so this term become positive, and from this you can easily find that your dV increases. Okay, and dV is greater than 0 from this relation. So here we get that velocity increases at the outlet for the case of supersonic diffuser. Then area increases because dA is greater than 0. Pressure decreases, as we already discussed in the previous slide, that if your velocity increases, your pressure decreases, or you can easily figure it out from the other relation, that is dA by A is equal to dP rho v square 1 minus Mach square. And if your pressure decreases, so your temperature also decreases and density also decreases. And if velocity increases, the Mach number also increases at the outlet. Okay, so this is the case for the supersonic diffuser. Now coming towards the third case. So now we have the supersonic nozzle. Okay, so the nozzle, again, we already know that dA is less than 0 for the nozzle. Mach number greater than 1 now because it is a supersonic nozzle. So if we just put all these things into this, so this term become negative over there. This term also become negative. So from here we can easily find that your dV is less than 0 for the case of supersonic nozzle. So velocity decreases, area decreases, pressure increases. So if velocity decreases, pressure also increases, and then your temperature also increases and density also increases in the case of supersonic nozzle. So now coming towards the case number 4. So in the case number 4, we have the subsonic diffuser. The subsonic means that Mach number less than 1. So if you can just figure it out that for the case of, this is for the diffuser. So diffuser dA is greater than 0. So Mach number is less than 1. So Mach number less than 1, it means this term is positive. dA is greater than 0, this term is positive, and your dV decreases, okay, less than 0. So your velocity decreases, area increases, pressure, if velocity decreases, your pressure also increases, and then temperature increases and density also increases in the case of subsonic diffuser, and Mach number decreases at the outlet when you are focusing on subsonic diffuser. Okay, so this all information come from the two equation which we already developed in the uh, previous lecture. Okay, so now this is just a summary and for all the story that I have just briefly told you. Okay, so these are the equations and these are the results which we are talking about: subsonic nozzle, subsonic diffuser, supersonic nozzle, and supersonic diffuser. Okay, so this figure is from your book. You just have to correlate with your book in order to understand it. Okay, so now coming towards some other important parameters related to the variation of fluid properties with the flow area. So we already developed some equations that is for the stagnation properties. So these equations we have already developed. Okay, so now here important thing is that what is the critical property? Basically, critical properties is a property when your Mach number is equal to 1. Okay, so and mostly Mach number equal to 1 at the throat area. For example, it is the nozzle. So in the nozzle, the throat is this area, and at this point your Mach number is equal to 1. Okay, and the properties that we have to define as at this point is critical properties, and we represent as T star, P star, rho star. If there is a velocity, it is velocity star. If there is a Mach number, it is Mach number star, and any other properties which we have to find at the throat area, or when your Mach number is 1. So it's mean we are focusing on the critical properties. Similarly, in case of converging diverging nozzle, your throat is this one, okay, at the center. So if we want to find any critical property, for example, if I can say in the problem statement, you have to find the critical properties, and I didn't mention which area I'm focusing on. So you just have to notice from the information that we are talking about throat, because at the throat we get the critical property, your Mach number become equal to 1. Okay, so you have to find T star, P star, rho star, and any other property, that is V star, at the throat, or you can say at the critical point. Okay, so now we have other relation, T star by T naught. So how this relation come from? Basically, just you have to put the Mach number equal to 1 in this equation, and the properties, then this becomes T star. Okay, so if you can just rearrange it, so T star by T naught is equal to 2 divided by K plus 1. Similarly, from the second equation, we get P star by P naught, and Mach number equal to 1. You have to put in the, you can say, equation number 2, and you will get this equation. And in equation number 3, if you can put Mach number equal to 1, so you will get this equation, that is rho star by rho naught. Okay, so these are the properties for them. This is how you have to define critical properties. So for example, if your stagnation temperature is known to you and specific heat ratio is known to you, so you can easily find T star, that is the critical temperature. You also have easily find, if the stagnation pressure is known to you, P star you can easily find, and stagnation density is known to you, so you can find rho star, or the critical density at the throat. Okay, so now we have other terms, that is mass flow rate and area by area star. Okay, so mass flow rate, basically this the derivation we will see in the coming slide. Okay, so for this time you just have to look at what is this equation. So we have area. So area, if area is defined, Mach number is defined at specific point, then stagnation pressure is known to you, stagnation temperature is known to you, specific heat ratio is known to you. So you can easily find the mass flow rate. Okay, and if I can say, you have to find the mass flow rate at throat. So it's mean the Mach number is 1 at this point. So by just putting the 1 value at the Mach number, so you will get the mass flow rate at the throat, and this was the maximum mass flow rate, because at the throat point we get the maximum mass flow rate. Similarly, if we want to find area by A star, okay, so area, for example, I can say this is the area at some part section. So I can say this is section number 1, and I want to find the ratio of area between this section to throat's area. Okay, so for this we can simply say A by A star, 1 by Mach, 2 by K plus 1, and then rest of the things are given over there. So if you have Mach number and specific heat ratio, so you can easily find A by A star. Okay, and from this, if I can say that this area is some 40 centimeters square, and I want to find throat area, so from this relation you can easily find out your throat area. Okay, so this equation, also the derivation of this equation, we will look into in the coming slide. Okay, so if you have any question, you can ask me, or then you can see the derivation as well. Okay, so now coming towards an other important point, effect of back pressure on mass flow rate, converging nozzles. Okay, so first important point is, what is the back pressure? Basically, back pressure is the pressure at the exit of your nozzle. So we can define as a back pressure, and sometimes we say exit pressure as well. And this P naught T naught is basically the inlet temperature or pressure. Okay, so for this case, we are trying to develop some graph between mass flow rate and the ratio PB by P naught. So PB is basically your back pressure and P naught is your inlet pressure. Okay, so for the case A, so in case A, that is mentioned over there, the point A, PB is equal to PE is equal to P naught. So if the pressure is same, so there is no flow. Okay, so no mass flow. So mass flow is zero. So for this, we just place this A on this line. Okay, so then we are moving towards case B and C. So case B and C. So what happened in this case is PB is decreased. So back pressure we have just decreased, and the mass flow rate increases, and flow is subsonic throughout, and pressure at the nozzle exit equal to back pressure. Okay, so the meaning is that, for example, if you just decrease the pressure, so your point become PB. Okay, so B point. Okay, so at B point your mass flow rate increases, and further if we just decrease the pressure, okay, and we can just take at point C after decreasing the temperature pressure, sorry, so your mass flow rate increases more, and this region is basically subsonic. Okay, so you already know subsonic meaning that your Mach number is less than 1 in this case, as it moved from B to C. And whenever your region is in between B and C, so you can easily say that your back pressure, so PB is equal to P exit. Okay, so this is the important point over there. Eventually, for example, we decrease the PB more as comparison to point C, and until it reaches to point number D, and at that point your Mach number is unity. So Mach number is equal to 1. So I already told you when Mach number is equal to 1, so the properties that are related to that point is basically critical property. So for example, we can say at point number D we have critical pressure or any other property. Okay, and this and the mass flow rate is maximum possible, and the nozzle is said to be choked. Okay, so here the important point is that if your Mach number become equal to 1 and you further decrease the pressure, that is back pressure, so your mass flow rate become maximum at this point, and with the decrease in further back pressure your mass flow rate will not be affected. Okay, so for example, if I can just decrease the back pressure more and the point reaches to point number E, so there is no effect on the mass flow rate. Okay, and the mass flow rate is maximum possible, so point D and E is referred to as a choked. Okay, so the meaning of choked is any point where your flow mass flow rate become maximum. Okay, so that point we can define as a choked. Okay, and for example, if in the problem statement I can mention that you have to find that whether your flow is choked or not. Okay, so the only thing is that you have to check that your P star is okay, so that I will define when we are going to solve the problem, so that you will get some understanding of it. So at this time you can just notice that if we can further decrease the pressure when your Mach number become equal to 1, so there is no effect on the flow, and your flow is called as a choke flow, and if it is at point number C and D, so the flow is not choked.
सर
Okay, जी
सर ये जो ग्राफ पे पॉइंट ए टू बी एंड बी टू सी है वो नोजल्स पे कहाँ पे हम उसको पॉइंट आउट कर रहे हैं?
अच्छा मैं आपको बताता हूँ। अच्छा, ये पॉइंट जो है ना बी सी, ये नोजल पे नहीं है, ये केसेस है बेसिकली। तो केस ए हमने लिया है, ठीक है, केस ए में हमने किया है बी पी इज इक्वल टू पी इज इक्वल टू पी नॉट। ये है केस बी, दिस इज केस सी, दिस इज केस डी, दिस इज केस ई। So these points are not on the nozzle. Okay, we are analyzing this graph for different cases.
ओके सर।
Okay, so we will apply this all things that is your choke flow in the problems as well. Okay, so first we will look into the equations that we are discussing in the previous slide, that is mass flow rate and area by A star, how these equations come from. Okay, so first we will try to look into the derivation of these equations. Okay, so in order to derive these equations, for example, if I want to derive area by A star, okay, so I will just take one case, that is converging diverging nozzle, and I can say this is your critical point and your Mach number is equal to 1 at the throat point. Okay, so in order to develop this equation, we can start from the mass balance, so mass flow rate balance. So rho VA is equal to rho star V star A star. Okay, so you already know rho VA, so rho is density, velocity and area at any point in this converging diverging nozzle, and rho star V star A star is at the throat area. So we just have to balance the mass flow rate. Okay, from this relation we can easily figure it out that area by A star is equal to rho star divided by rho into V star divided by V. Okay, so if we get the values of rho star by rho and V star by V, so we can easily find the value of A by A star. Okay, so how we can find out the rho star by rho value? So first we will find the rho star by rho value. So rho star by rho value is rho star rho naught into rho naught over rho. So if we can write this equation as, so the meaning is same, that it becomes rho star by rho. So rho star by rho naught value we have just looked in the previous slide. Okay, so if you remember that rho star by rho naught value you can easily get from the stagnation temperature stagnation density equation by putting the Mach number equal to 1. So 2 divided by k plus 1, 1 k minus 1. So this equation we already see in the previous slide, and rho naught over rho we already know that 1 plus k minus 1 divided by 2 Mach square and 1 divided by k minus 1. Okay, so simply you have to put these values, two equations into, you can say, equation number 1. Okay, and if you can multiply these two equations, I'm just going to write the final term, so you have to do the multiplication by yourself. So the final equation for rho star by rho become 2 k plus 1, 1 plus 1 by 2 k minus 1 Mach square one divided by k minus 1. So this is the value of rho star by rho. So we have the value, and now we have to find V star by V. So in order to find V star by V, so simply you have to do is that V star by V is equal to, we can say that KR T star, that come from the, because at V star, because it's a critical point, so your speed of sound and your local velocity is same at this point because Mach number is 1. So we can simply write KRT star 1 by 2 divided by V. And if we can just further simplify this equation, or we can write in another form, so we can easily write as KRT 1 by 2 V T star by T naught 1 by 2 T naught by T 1 by 2. Okay, so we can write, and the result will be same as this equation. Okay, so now we can get this value from the previous slide. We already know that T star by T naught value and T naught by T value is also known to us from the stagnation properties topic. Okay, so we get these values and simply put into this equation, and the final equation become, so I'm just going to write the final equation, V star by V is equal to 1 over Mach 2 k plus 1 plus 1 by 2 k minus 1 max square 1 by 2. Okay, so this is the final term for v star by v. After putting t star by t naught value and t naught by t value, you can say this is equation number 2. Okay, so now we have two values, so you simply put these value in the equation which is here. So you can easily find a by a star value. So you can note it down and then we will move towards the next slide. And if you have any question, you can also ask me. So your a by a star become, after putting these values, that is p star by p and v star by v. So the final equation is 1 by Mach 1 plus 1 by 2 k minus 1 max square so this is the final equation for a by a star. Okay, and in the same equation, so if you put all the values of k, so you can simplify this equation and you can use it directly. So if in case the area at some section of your converging diverging nozzle is known to you and you have to find the throat area, so you can easily find, and if the throat area is mentioned and you can find the area of specific section, so you can also easily find if the Mach number is known to you. Okay, so this is the equation which we already see. So this is just a derivation, quick derivation, just for your understanding. So we will try to develop another equation for the mass flow rate as well. So you can note it down and then I will move towards the next part. And all these difficult formulas I will try to give in the exams as well. Okay, by the given in the in the question paper with the formula sheet. Okay, you do not need to remember all these equations. And I will also pass these formula sheet to you by I think 2nd of July. Okay, so that you will correlate it with that which formulas are given in the exam papers and which formula you have to remember it by yourself. Okay, so I will pass at the to all the class on 2nd July. Okay, so now here we have to develop the mass flow rate equation. So mass flow rate is basically equal to rho AV. Okay, so if we can just simplify this equation, so we can also write that rho is basically P by RT area and your velocity is Mach number into under root KR T. So by just simply putting all the values, we get this equation. And if we can just further simplify it, so your equation becomes PA mark under root K divided by RT. So this is just a simplified version of this equation by just doing some mathematics. So you can easily find out this is the result. Okay, so now from here we have to put the value of P in this equation and T in this equation. So where we get the value of P and T. So these P and T come from the stagnation properties equation. So P naught by P, you already know, 1 plus K minus 1 divided by 2 Mach square K divided by K minus 1. From here, if you want to find the P value, so simply you can take this P on the right hand side, and this whole term become in the denominator. So P naught divided by 1 plus K minus 1 divided by 2 Mach square bracket K divided by K minus 1 is the value of P. So similarly, so you can find the T value from T naught by T 1 plus K minus 1 divided by 2 Mach square. So we can easily find this value from this equation. So after finding this value, you have to plug in, you can say equation number 1, and your final equation become m dot s area mac P naught K divided by RT naught divided by 1 plus K minus 1 Mach square divided by 2 K minus 1 divided by 2 K minus 1. Okay, so this is the equation. So if we can just put the value of Mach number is equal to 1 in this equation, so you will get the mass flow rate maximum. Okay, and mass flow rate maximum, and also you have to replace this area by A star, because the mass flow rate maximum is at the critical point. So the area that is related to this is at the critical point, that is A star P naught under root K R T naught 2 K plus 1, and then the power is, okay, so power I am going to write in the bottom, so K plus 1 divided by 2 K minus 1. So this is the equation for the maximum flow rate. And for example, if I can say you have to find the mass flow rate and your flow is choked, okay, so you can just simply apply this equation, that is maximum mass flow rate, because I already told you that when the flow is choked, your flow rate become maximum. Okay, so you can apply this equation. Okay, so you can note it down and then move towards the next part. Okay, so we will take 10 minutes break and then we will again continue from this topic. Okay, so starting again. So first I will just correct something. Okay, so in the previous slide I have write this value as k minus 1. Okay, so this is basically k plus 1. So just you have to correct it that here this is plus 1 and in the denominator it is minus 1. Okay, and this equation is from your book, which is equation 17-24. Okay, and the maximum is also mentioned over there, 17-25, so that you will easily correlate with it. Okay, so coming towards the first example, so this is from your book. So here it is mentioned that the geometry that is in figure 17-19, that is converging diverging nozzle. So you have to calculate the critical pressure and temperature of carbon dioxide for the flow condition described. Okay, so example 17-3 we already practiced, and this is example 17-4. So the stagnation pressure and temperature come from the previous example. So our main uh, things that we have to determine is P star and T star at the throat location. Okay, so you have to note down the data and then we will see how to solve it. So I'll just randomly draw the converging diverging nozzle. So here we have the stagnation pressure, which is 1.4 megapascal, and we have stagnation temperature as 473 Kelvin. So our main target is to find the properties P star and T star at this location, and inside we have CO2. Okay, so in order to find the P star T star, we can simply apply the relations that we already see, that T star by T naught is equal to 2 K plus 1. Okay, and if we have the K value, and K value for carbon dioxide is 1.289. So if we put the value to 1.289 plus 1, so it will be equal to 0.8737. Similarly, we can find P star by P naught, that is equal to 2 K plus 1 K divided by K minus 1. So you have to put the value of K and you will get the answer as 0.5477. So from these two relations, we can easily say that your T star is equal to 0.8737 into T naught, and P star is equal to 0.5477 into P naught. So T naught and P naught is mentioned in the problem statement. So you just have to put the value and you will get the, so T naught is 473. So the value is 413 Kelvin for T star and 0.5477, and P naught value is 1.4 into 10 raised to power 3. You just have to convert into kilopascal, and now it's become equal to 767 kilopascal. So we have P star and T star value with us. So this is the required thing which we have to determine from this data. So the solution is completed. If you have any questions, you can ask me or you can note it down. Then we'll move towards the next part. Coming towards the next question, which is 17-5 example from your book. So you have to read the statement first. So air at 1 megapascal and 600 degrees Celsius enter a converging nozzle that is shown in figure 17-24 with the velocity. Initial velocity is mentioned. So you have to determine mass flow rate through the nozzle for a nozzle throat area of 50 centimeters square when the back pressure is A part 0.7 megapascal and B part 0.4 megapascal. So this is the question and the figure is mentioned, so you have note down the required data and then we will see how to solve it. Okay, this is your geometry. So from here, our main thing is to find your mass flow rate. Okay. So in order to find the mass flow rate, first thing required is to either find that your flow is choked or not choked. And how we can find that your flow is choked or not choked? We have to find the ratio back pressure by P naught. Okay, and in order to find this, we need the value of stagnation pressure first. Okay, and that's why first thing is to find the stagnation pressure. So stagnation pressure, you already know that T naught, because in order to find the stagnation pressure, we need stagnation temperature first. So T naught is equal to Ti plus Vi square divided by 2 Cp. So this equation we already know from the previous knowledge. And here we have the Ti with us, which is 600 degrees Celsius. So you can say 873 Kelvin. Vi square 150 meter per second square 2, and air Cp is 1.005 and it is in kilojoule, so you have to convert into joule by multiplication of 1000 and the end result is 884 Kelvin for stagnation temperature. Now from this data we can easily find the stagnation pressure, which is P naught is equal to Pi T naught divided by Ti K divided by K minus 1. So we have Pi with us from the problem statement. T naught we have just find, that is 884 Kelvin. Ti is 600 degrees Celsius and that is 873 Kelvin, and K value for the air we already know. So simply you have to plug all the values. So Pi is 1 megapascal, T naught is 884 Kelvin, Ti is 873 Kelvin, and 1.4 minus 1. So if you can solve it, you will get the value as 1.045 megapascal. So now we have P naught value with us. Okay, so in order to find, so you have to note it down, then we will start with the part A. Okay, so I will just go back to the graph. So I've just showed it to you in the previous slide. Okay, so from here, how we get to know that our flow is choked or not choked? So I already told you, this is your, for example, at point number D, we have the ratio that is P star by P naught. And at this point, we have PB by P naught. So your flow is choked if this PB by P naught value lies in this region. Okay, so if it lies in this region, it is choked. And if your PB by P naught is lies in this region, so it is not choked. Okay, so for this we can easily say that if PB by P naught is greater than P star by P naught, so our flow is not choked and it is a subsonic flow, that is mark number less than 1. Okay, and at this case our exit pressure is equal to back pressure if PB by P naught greater than P star by P naught. However, if PB by P naught is less than P star by P naught, so your mass flow rate is maximum. So if we have to find the mass flow rate, so simply you have to apply the relation, that is maximum mass flow rate, in order to find the uh, flow rate if your PB by P naught less than P star by P naught. Okay, so this is the important point because this we have to apply in the example as well. Okay, so coming towards the part number A, so we have to find mass flow rate when your back pressure is 0.7 megapascal in the part A, and we have to find mass flow rate. Okay, so first we can find the PB by P naught. So P naught we already find. So PB value is 0.7 megapascal. P naught value is 1.045 megapascal. So you can take the ratio of these. It will be 0.670. Okay, so now we have to find P star by P naught as well. Okay, because if we have that value, then we can find that either your flow is choked or not choked. So P star by P naught, that comes from the equation that is 2k plus 1 k divided by k minus 1. Okay, so simply you have to put the value of k, that is a, and you can find that it is equal to 0.5283. So in this case we have PB by P naught is greater than P star by P naught. So it's mean overflow lies in subsonic region, and it is that your throat pressure, or you can say exit pressure, is equal to back pressure. Okay, so this is the main important point, and from this data we can figure it out. Okay, so another important point is that in order to find your mass flow rate, for example, if I can say mass flow rate, that is equal to rho at throat, area at throat, and velocity at throat. Okay, so we do not have the value of temperature at throat. So if we have the value of temperature at throat, then we can find the velocity at throat. Okay, and also we do not have the value of rho throat with us because in order to find rho throat, we need the pressure at throat. So pressure at throat is PB, but temperature at throat still we have to find. Okay, so first thing we have to look into the values, that how we can find out this temperature at throat, and um, next thing is, okay, so temperature and pressure at throat is known to you, and rho throat we can easily find. Okay, so first thing, so you have to look for one value, that is pressure at throat over stagnation pressure. So stagnation pressure at throat, basically this is I'm talking about case number 1. So 0.7 megapascal. So we already know that flow is not choked. So pressure at throat is equal to back pressure. So the back pressure value is 0.7 megapascal, and P naught value is 1.045 4, 5. So from here we can get to know that Pt by P naught is equal to 0.670 for the first part. Okay, so by using this data, simply we can go to thermodynamic table and find some data from the thermodynamic table. So which table we have to look into? So we have to look into the table A32. So it is mentioned one dimensional isentropic compressible flow function for an ideal gas. So here if you can notice that the Mach number is known to you at different Mach number. Okay, so this I will tell you later that what is the value of this Mach star. A by A star. Okay, so if we want A by A star, we can easily find against these Mach number, and then P by P naught, rho by rho naught, T by T naught. And this P is basically your exit pressure. Okay, so that is your throat pressure, you can say, and throat density by stagnation density, and temperature at throat over and stagnation temperature. And these all values come from these formulas which are mentioned over there. So simply you have to plug in all these values and you will find out. But for our easiness, the table is mentioned, so we can easily find these values. So in this case, the Pt by P naught is known to us. So Pt by P naught we have already find that is 0.670 for part A. So you have to look into it that where this value lies. So 0.670 lies in between 0.7209 and 0.6560. So it's mean this value is in between. So you have to apply the interpolation to find the value of T by T naught. Okay, so first interpolation T by T naught, and also you have to apply the interpolation to find the Mach number as well. So your Mach number is also in between, I think 0.7 or 0.8, in between 0.7 and 0.8. So you have to apply two interpolation by using Pt by P naught value. Okay, so I'm just going back to the slide again. So Pt by P naught value is known to us. So 0.670. So from thermodynamic table, we get some values, that is throat temperature over stagnation temperature as 0.892. So this come from interpolation, and then again interpolation, you get the Mach number at the throat as well, which is 0.778. Okay, so by just applying the interpolation. So now we have these two values, so we can easily find the throat temperature from this data. So throat temperature is basically equal to 0.892 into stagnation temperature. So stagnation temperature is 884 Kelvin, and now we can find out the throat temperature as 788.5 Kelvin. So this is our throat temperature. So similarly, we need the throat density as well. So that is throat pressure over R and throat temperature. So throat pressure is basically equal to back pressure, so 0.7 megapascal or 700 kilopascal. R value is 0.287, and temperature at throat we have just found, which is 788.5 Kelvin. So if you can just solve it, you will get the density at throat, which is 3.093 kg per meter cube. Okay, so from this data we can easily figure it out the value of V throat. So V throat is basically Mach throat into C throat. C is speed of sound at the throat. So Mach throat we already find by using interpolation, and by using this data we can say that 0.778 under root 1.4. R value is 0.287, and multiplication by 1000 to convert into joule, and then temperature at throat we have already find, which is 788.5. Okay, so by using this data we can easily find the velocity of at throat, which is 437.9. Okay, so from this we can find the mass flow rate now. So rho throat, area throat into velocity throat. So area throat is mentioned in the question, which is 50 centimeters square. So you just have to multiply all these three terms. So 3.093 into area throat is 50 into 10 raised to power minus 4. Velocity at throat is 437.9. So if you can multiply, you will get the mass flow rate as 6.77 kg per second when your back pressure is 0.7 megapascal. So this is the solution of part A. If you have any question, you can ask me. So then we will move towards the part B as well.
सर
जी
सर ये टेबल से डाटा किसके अगेंस्ट निकाला है वो तो दोबारा बता दीजिएगा।
अच्छा मैं आपको बता दूं। अच्छा हमने सबसे पहले किया है कि हमने पी टी बाय पी नॉट फाइंड किया है। ठीक है, सबसे पहले आपने केस फाइंड करना है कि ये चोक फ्लो है कि नहीं है। ठीक है, अगर चोक फ्लो नहीं है तो आपका जो एग्जिट प्रेशर और बैक प्रेशर के इक्वल आ गया और आप इजीली पी टी बाय पी नॉट निकाल सकते हैं। ठीक है, जब आपने पी टी बाय पी नॉट निकाल लिया देन आपने थर्मोडायनेमिक टेबल 832 में जाना है। ठीक है, यू हैव टू चेक this line which is p by p naught, okay, and look for the value that is 0.670. So 0.670 lies in between these 2 points 0.7209 and 0.6560. So the procedure is same, you have to apply the interpolation between these 2 points and you have to find the value of t by t naught first and then Mach number as well. Okay, so Mach number is in between 0.7 and 0.8. Okay, so once you know these two values, Mach number and t by t naught, so then the procedure is mentioned in the slide as well. Okay,
सर ये तो समझ आ गई, लेकिन वो चौक नंबर और जो एग्जिट पे प्रेशर था उसका क्या दोबारा बताइएगा, वो इक्वल या उसकी समझ में
अच्छा मैं आपको बता देता हूँ। अच्छा, जब भी आपको बैक प्रेशर दिया हुआ हो तो सबसे पहले आपने फाइंड करना है कि आपका फ्लो चोक्ड है कि नहीं है चोक्ड। How you have to judge that your flow is choked or not choked? So the value is that if PB by P naught is greater than P star by P naught, so it's mean that your flow is not choked. Because if you can notice that if this value is greater, so it's mean this lies in this area, and this is the area where there is a subsonic flow and the pressure at the nozzle exit equal to the back pressure. Only for this case, when your PB by P naught is greater than P star by P naught. Okay. Other case, for example, if this is your case that your PB by P naught is less than P star by P naught. So it's mean for this condition, this value lies in this region and this is the area where the flow is choked. So choke point is from point D to E. Okay, because at this point we have the maximum flow rate, because after Mach number 1, if we further decrease the back pressure, we have no effect on the mass flow rate, and when there is no effect on the mass flow rate, and at that point we have maximum mass flow rate, and that point is called the choke flow. Okay,
ओके सर।
okay, so we will look towards the part B, so you can easily find out the meaning of the choke flow, because part B is basically related to the choke flow. So in the part B, we have mentioned that in the problem statement that PB is equal to 0.4 megapascal. Okay, so for this, first we have to find the, and our main target is to find mass flow rate. So first we can find PB by P naught. So PB by P naught value is, because back pressure is 0.5 megapascal, P naught value is 1.045. So from here we can find that PB by P naught value is 0.383, and P star by P naught value we have already find in the last or part A. So P star by P naught is equal to 0.5283. So from here we can easily figure it out that PB by P naught is less than P star by P naught. Okay, so from there you can say that your flow is choke now. Okay, because your PB by P naught is less than P star by P naught. And if your flow is choked, so your mass flow rate is maximum. And for maximum mass flow rate, we can simply apply the maximum flow rate equation. We already find in the and we already derived as well. That is A star P naught under root K R T naught to K plus 1 K plus 1 to K minus 1. So this equation we already derived. That is for the maximum flow rate. And if your flow is choked, you can simply apply this relation, okay, directly. So we have the value of A star with us because the throat area is mentioned. Stagnation pressure we already find. K value is known to us. R value is known to us. T naught we already find. And these are the K values. So just you have to put all the values and you will find that your mass flow rate is equal to 7.10 kg per second, and that is the mass flow rate maximum, and that is related to the back pressure equal to 0.4 megapascal. So this is the solution for part number B. Okay, so if you have any question you can ask me or you can note it down. Okay, so at this point we will stop, and you have to solve this question again by using area as 40 centimeters square. Okay, so you have to repeat all the step, and you can easily solve it. So if you have any question you can ask me, or otherwise you can note down the data and then we will just solve.
एक्सक्यूज मी सर।
जी,
सर हमारा कोर्स कब तक कवर हो जाएगा?
आपका कोर्स तकरीबन बस अभी ये इस वीक हम ये ख़त्म कर लेंगे कंप्रेसिबल फ्लो, और उसके बाद एक लास्ट टॉपिक रह गया तो फिर ख़त्म हो जाएगा।
सर मतलब 28 से पहले पहले हो जाएगा कवर, नहीं हमें लास्ट वीक में भी क्लासेस अटेम्प्ट करना पड़ेंगे?
क्लासेस तो आप लोग अटेम्प्ट करेंगे जब तक जो है ना वो कोर्स चल रहा है, जब तक ऑफिशियल, क्योंकि आपकी क्लासेस तो 2 जुलाई तक है ना आई थिंक।
यस सर।
हाँ जी, तो लेकिन कोशिश करेंगे उससे पहले पहले ख़त्म कर लेंगे कोर्स।
ओके सर।